Welcome back, and let's work on the interesting concept which compares displacement and distance. Sounds the same to me. Definitely both means that we are walking or traveling from place to place and we want to measure how far did we go. Well, apparently those things can be different from physical and logical point of view. For now, let's just review that if s of t is called the position at time t, then you guys know that s prime, or derivative of s, is called the velocity at time t, v of t. If you take a second derivative of the position, or the first derivative of velocity, you get acceleration at time t. Not too bad, we know that. Well, now we know integration, and also we do know now fundamental theorem of calculus, part 2. That's the one when you plug the top minus the bottom, so with the one with the bar notation. If you're revising this point of view and using entire derivatives, since position s of t is an entire derivative of velocity v of t, and we can use fundamental theorem of calculus now. From a to b, that means we're traveling from a to b, right? So we're traveling from a to b, then knowing velocity, how to find distance. That's right, let's just integrate it. That's a definite integral of function velocity from a to b with respect to time t. The entire derivative of v, that basically means we're going from here to here, reversing the process, is position function s of t, but from a to b. So we plug the top minus the bottom, we know that. That's fundamental theorem of calculus, part 2, FTC. But s of b minus s of a represents the net distance traveled. And that's a new thing to remember. Net distance, or net change, or displacement, that's what we start with. We're starting with learning what displacement is versus distance of the object during the time interval is the difference in locations at the end and the start of the period. Not very clear to me what it means, but basically this is what we're getting from this formula. From this formula, we learn how far did I move out away from the original point. So for example, the A point was, say, my bed. Then I was going to leave the apartment, to the door. So I walked to the door first, from left to right, completely from A to B. And then I remembered that I forgot the key. So I came back. And the key were here, say, at the drawer, right? Or in some kind of top cover of the kitchen, and some kind of top counter. Then I picked up the key and then I still left. This is still the integral from a to b, is just in pieces now. It's from a to b, from b to c, and then from c to b. But as you remember, integral from a to b can be broken down into integral from a to, so we have pieces here basically. From b to c, going back, then going back. Since this distance is the same from b, I would do like this. The integral from b to c equals minus integral from c to b. So these did not even go into calculations if you think about that. But I did walk. So the integral of velocity from a to b gives me the displacement. That's what we call displacement, which means how far I am from bed to door. That's the displacement, how far I am left from bed to some kind of location. In this case, it's door. But it doesn't show me how much I actually walked. I did not walk just from bed to door. Maybe I was circling in the apartment with my shoes on, like we always forget something and keep going back. So that means it doesn't give me how much I walked. This idea of how much I walked is called distance. Distance, or total distance traveled, that's what we call now. Total distance traveled, on the other hand. Rather than the net distance traveled, This is the area problem now, because now we want to have only positive changes. So we don't want this change to be negative, this one from B to C. We don't want this change to be negative. So we want to compute absolute values instead to make sure that everything we're computing is positive. Why they're saying it's an area problem? I will show you over here. So the first piece, that's the displacement. I will call it A. The first piece, that's A. And the second piece, that's distance. I will call it B. A is shown over here on the top. When I traveled from one place to another place, maybe I came back. And when I came back, that different direction makes the area negative. So when I'm integrating velocity, I'm looking at the area below the function. But the function might be below x-axis, then the area is negative. The net change, that's what we're going to call net change. The net change assumes that this area is positive and this area is negative. That's how we know it. So when I add up two areas, I just know how far I am from the original point. From bed, I am this far to the door. But it doesn't show me how much I actually traveled. So the displacement is a1 minus a2. That's exactly the definition of the definite integral. For the distance though, I want to know how much I walked. So instead of assuming that this area was negative, I will take absolute value of that area. Then I will add them together. And then on the example of traveling, it will give me this type of answer. It will give me the answer. I traveled from the bed to the door. Then I came back from the door to the top of the, whatever I just said, table where my keys were. Then I traveled from that location to the door back. And I will add all these traveling parts because now I'm taking absolute value of them, instead of thinking that this direction over here from B to C was negative. Make sense? Then in this case, this gives me, instead of displacement, which says how much I displaced myself from the original point, this will give me the distance, how actually much I walked or I was driving in the car and so on, without assuming that the direction can be positive or negative. And let's show you here on the example. Oh, the little summary before we do the example. Maybe pause the video to read this carefully, but basically we're reviewing again the position of an object moving along a line at time t, which is s of t, is the location of the object relative to the origin. Well, velocity will be the derivative of the position with respect to time t. Then A is displacement. Displacement of the object between A and B, both are positive, is a definite integral of the velocity, and it is s of b minus s of a based on the FTC, fundamental theorem of calculus. This distance traveled, or speed, or distance traveled, or also we call it just distance actually, yeah. By the object from t equals a to t equals b, that will be the absolute value from a to b. That will show me how much I actually walked without assuming negative or positive walking or driving, negative, positive directions. So the absolute value of v is the speed of the object versus velocity. That's a good point as well. So velocity can be positive and negative if you think about that, right? The speed can be increasing or decreasing. But that's velocity has a sign, so can be plus or minus. Then displacement has a sign as well, plus or minus. However, the speed has no sign. Speed is 55 miles per hour. We don't assume there's a speed of minus 55 miles per hour. So only positive or zero, right? That's why displacement, no, that's why distance traveled is only only positive or 0. That's kind of the idea. These two are connected and these two are connected. Great, let's do the example. You might see this example in your homework or in your exam, where we want you to understand the difference, especially if you're physics major or engineering major. That's something you definitely need to understand really well. In this example, the velocity of a particle moving along a horizontal line is given by the function t squared minus t minus 6 meters per second after t seconds. Find both displacement, that's how much did I actually end up to be away from the original point, and then find distance, that's actually how much I walked, or in this case, well, maybe I was driving, doesn't matter, traveled by the particle during the interval from 1 to 5. Interval from 1 to 5 gives you the hint that we will create integral from 1 to 5. Solution. And just like in definition, I will code A and B. A is the simple one because it has no absolute value in that one. And for A, I will just create the integral from 1 to 5 v of t dt. Remember, t is a dummy variable. If you want, you can use x dx, but in this case, t actually means something. It means time. So it's just nice to use the same notation. That will be s of 5 minus s of 1, right? We just need to calculate those. Okay, integral from 1 to 5. T squared minus t minus 6 dt. If you want, you can put parentheses like this. What is antiderivative of this polynomial? Fast integration tells you that you don't have to break this polynomial into 3 pieces. Just remember, t squared gives you t cubed over 3 minus t gives you t squared over 2 minus 6 gives you negative 6t, a bar from 1 to 5. Carefully plug in 5 everywhere first. 5 cubed over 3 minus 5 squared over 2 minus 6 times 5. Put parentheses, negative sign, that comes from the formula. Top minus the bottom. Top minus the bottom. Put parentheses. These parentheses will be very important for you not to make mistakes. Plug 1 everywhere. 1/3 minus 1/2 minus 6. And in this case, I have it in my notes, if you carefully calculate all the fractions, you will get 16 over 3, which is approximately 5.333. Since this number is positive, again, this number can be negative. So note 1. Answer here can be negative. Note 2. Our answer, so 5.333 meters for, we're looking in this case, displacement. I would say like this. Displacement equals 5.333 meters means that the particle is located. So it tells you location of, that's why it's called displacement. It tells you where the place of the particle is. Located 5.333 meters. Is it in meters? Yeah, meters to the right. To the right. If it's negative, then to the left. So we don't know how much the particle traveled from 1 to 5. Maybe the particle came here, then came back, and so on and so on. Oh, that's actually 1 and 5, it's time. So that's not the interval. From 0 to infinity. So the particle keeps traveling following the velocity function t squared minus t minus 6. And then the time we measure is from 1 to 5. So maybe it came back a couple times, and then it came, and then it kept going, and then it stopped at 5, or maybe not stopped, but at least our recording stops when the particle is 5.333 meters to the right. If it goes to the left, then it's negative. Make sense? So B will calculate those using absolute values. And now it will reveal the secret. If the answer is the same, then the particle was just moving to the right all the time. But if the answer is different, and the spoiler alert, it is going to be different, then it means the particle was actually moving in circles sometimes, and so on. And that should be taken into account. For B, we're going to calculate distance. So how much the particle actually traveled. To calculate that, we need to take into account that the particle might be traveling left and right. For this, we need to take into account where the velocity can be positive or negative. Take the function of the velocity, which is t cubed minus t minus 6, and find the roots of the function, because those roots will identify where the function is negative or positive. The function has two roots, 3 and negative 2, but on the domain, on the interval we're looking for from 1 to 5, we only need t equals 3, which makes sense. We don't want to have negative time anyways. Now I'm going to create a signed line for the original function v, not its derivative. No, just a signed line. V, and I will be like this. This is my t. I want to know where my v is positive or negative. T is considered from 1 to 5. That's what they told us at the beginning. And we know the root 3. This root 3 means at some point velocity was 0. Do you understand that? Because it basically means that velocity may be positive or negative, but at 3 it touches the t-axis, not x-axis, t-axis. So at t equals 3, velocity is 0, because when you plug t equals 3 into this equation, v is 0. So v actually is a cubic function. And at some point, as you can see, at 3, it's going to be 0. So our job is to know, was it positive, negative, or maybe both positive, or maybe negative, negative, and so on. Since this 3 is the only root on the interval from 1 to 5, we definitely can only just take test points at any place, and these test points will reveal the sign of the function on that interval. That's because this function is continuous, it's a cubic function, and there's no way it was positive, then disappeared, and then appeared to be negative somewhere. Since it's continuous and it's going through 0 point at time 3, then on the left from 3 and on the right from 3, it has only one sign. Let's check. For example, at 2. What happens in 2? I'm going to put 2 here into the box. I actually like the factored form better. If I plug 2 over there, it gives me 2 plus 2, that's positive. 2 minus 3, that's negative. So over here, velocity in blue, v of t, is negative. It's going down, decreasing. Velocity is decreasing. Here I will check 4. Plugging 4 into this box again, 4 minus 3 is positive, 4 plus 2 is positive, so positive. That means on the graph of the function, here's graph t, here's v of t, and here's 3. The function was first negative, and then it became positive. That's the idea. Then the area over here, from 1 to 3, the area is negative. From 3 to 5, the area is positive. The previous way, when we differentiated, we found net area, positive area minus negative area. That gave us displacement. If I want to calculate, like on this picture over here, only positive areas, like here you see, to calculate only positive areas, to have A1 plus A2, to know how much actually I moved, left, right, positive direction, negative direction, then I need to apply absolute value on both sides. If the side used to be positive originally, absolute value will not change anything. But in our case, this piece is negative, absolute value of the negative makes it positive. Then we're going to add positive numbers. Let's finish this example. So now we know, we can conclude that v of t is negative from, well, I will do negative. I can do even negative and 0. From 1 to 3, it's negative or 0. No. Negative on 1 to 3. And then velocity becomes positive or 0 on 3 to 5. Nice. Then the definition of displacement is going to be integral from a to b from 1 to 5. Absolute value, I will put it even in red color. Absolute value of the velocity function dt. And absolute value only is going to change the first interval. The first interval from 1 to 3. So we're going to have 2 from 1 to 3 and then from 3 to 5. Make sense? The second one stays the same. It's still t squared minus t plus 6 and dt. This one we actually integrated already. We just need to plug different numbers now. But the first part is now going to be minus, I'll put it in blue, minus t squared minus t plus 6 dt. Why? Because that's the definition of absolute value. Absolute value makes negative things positive by putting a negative sign in front of it. Make sense? So, okay, I found a little formula for you because I'm pretty sure you did not really catch what I just said. Here it is. It's the formula for the absolute value function. So the absolute value function gives you the same thing if your input was positive or 0. But if it's negative, then you have to put negative sign in front of it. And that's how you make sure that the result is positive. That's why this red piece is important, red negative sign in front of the function. Because we just learned that from 1 to 3, the function is negative. I also just realized that why I'm showing you this nasty graph over here, if I could just plot it nicely. And you know what? I mentioned once it's a cubic function, but actually it's not. The original function is squared function, t squared minus t minus 6. Did you question this? How did they get these nice solutions from the cubic function? Well, it's quadratic actually, I just caught a mistake. Here it is, it's a parabola. A parabola, and we're looking at this parabola on the interval from 1 to 5. From 1 to 5, indeed, it crosses x-axis, well in this case it's t-axis at the root 3, so at 3 it's 0. And indeed, it is negative from 1 to 3, and then it is positive from 3 to 5. That's what we did for A. For B, we want this negative piece to be positive instead. And that's what we're applying absolute value on that interval from 1 to 3. From 1 to 3, we're using absolute value of v of t. This is function v of t. So it basically reflects the area up to make it positive. And now we're going to add those two positive areas. Let's finish calculations and you'll see that we're almost done. Now we start finally integrating. The first one, I will recommend you to just distribute the negative sign, minus t squared plus t minus 6. Now you can integrate. That's going to be negative t cubed over 3 plus t squared over 2 minus 6t. And this is different unique integral. And this integral, we are working with lower limit of integration 1 and upper limit of integration 3. Plus t cubed over 3 minus t squared over 2 plus 6t brackets. And this is the second integral with 3 and 5 limits of integrations. That means each integral will give me a couple, top minus bottom, top minus bottom. So the pink will be the first one. Minus 3 cubed over 3 plus 3 squared over 2 minus 6 times 3, that's just the top, minus plugging everywhere 1 minus 1/3 plus 1/2 minus 6. And that's the pink part, the first integral. The second integral will be orange. And as you can see, we're adding those two. So plus orange piece. That one will be everywhere plugging 5 like we did before in A. 5 cubed over 3 minus 5 squared over 2 plus 6 times 5. That's the top part. Minus, now plugging 3 everywhere. 3 cubed over 3 minus 3 squared over 2 plus 6 times 3 brackets. And that's the second integral. You don't have to do it so complicated. You can actually call it integral 1 and integral 2. I saw many times notation like this. They call it I1 plus I2. And you can just calculate I1 separately and then I2 separately and then add the results. If you like this notation, just do this way, that's fine as well. But at some point you will see that you will become so experienced with integrating functions that you don't have to break them in pieces and you can do it all in once. Now grab your calculator and add those areas. The pink piece I calculated, the pink piece is 22 over 3. The orange piece plus orange is 38 plus 3. The final result is 60 over 3, which is 20 meters. Let's compare with the previous result. The previous result was some kind of fraction, 16 over 3. 16 over 3, here it is, and that's 5.333. So it means we know that the particle relocated to 5.333 to the right? So now the location, or you can say the coordinate of the particle is 5.333 meters to the right. But to get there, the particle was actually moving right and left, right and left, right and left, and it moved. How far did it move? So we're looking for distance. We're answering the question, the distance. How much this particle walked, or it was flying, or it was running. It actually moved, so distance, by 20 meters. So that's distance. Very interesting idea. And the answer for the first question, 5.333, that was net change. Net change is when you assume negative and positive directions. So you have 0 going to the left at any time is negative, going to the right at any time means positive. That's the idea of the net change, assuming that areas below x-axis are negative, above x-axis are positive, like on this graph. But distance wants to add all changes, regardless of the sign, to know the complete change. So that's a total change. Total distance traveled. Total distance traveled says, let's use the same result we had from integration, but apply absolute value for all the negative displacements, because displacement can be negative. Take the number for displacement. Say displacement was -7. That means I walked 7 meters to the left. Apply absolute value to that displacement and it becomes +7, and then add to the positive displacements you had before, and that gives you the total positive displacement. So I walked for 20 meters after all, but I am 5.333 meters away from the beginning. Hope this example was not too complicated, and I think it's pretty exciting to finally get into some physics and engineering, especially if you're going to go into the STEM major, aerospace engineering, and so on. That will be part of your career. So dive into this topic and hopefully enjoy it, because I think it's pretty cool. Well, see you next time.